The 12th anomaly has arrived, and with it a tremor that has rippled through astronomy, because observers studying the interstellar comet 3I/Atlas have reported behavior that seems to snap the rules of ordinary comet physics in half. What they have seen, and what astrophysicist Avi Loeb has highlighted in recent analysis, is starkly simple to describe, yet profoundly hard to explain. The comet's jets keep pointing in the same direction in space, crisply aligned and unsmeared, even though the nucleus itself is rotating. In any normal comet, jets are produced when volatile ices near the surface heat up and sublimate, venting gas and entrained dust outward like geysers. If the body spins, the vents rotate with it, and the jets should sweep around, tracing curved or spiral patterns and creating a smeared fan over the course of a rotation. 3I/Atlas rotates roughly once every 16 hours, a tempo fast enough that fixed vents should produce obvious changes in jet direction across a single night of observations. Yet, that is not what telescopes are recording. Instead, successive images show jet streams extending more than 1,000,000 kilometers from the nucleus, while holding a narrow, unwavering aim for hours and even days, as if they were locked to an inertial frame completely indifferent to the comet's spin. These are not faint, ambiguous wisps that could be dismissed as imaging artifacts. They are long, bright, highly collimated plumes traveling at hundreds of meters per second, so geometrically stable that they look less like ordinary outgassing and more like straight beams etched into the dark. The contradiction is what makes the anomaly so unsettling. A 16-hour rotation period means any vent fixed on the surface should sweep a full 360 degrees in that interval, effectively painting a cone of material into space. Given that ejecta move outward at around 400 meters per second, even a modest rotational shift should bend the flow measurably. Over multiple rotations, the jets should blur into a diffuse halo. Instead, they retain their sharpness across repeated sessions, suggesting either that the jets do not originate from simple surface vents or that something is counteracting the rotation with uncanny precision. The effect is like watching a spinning garden hose whose stream stays perfectly straight even as the nozzle turns. Possible to imagine, nearly impossible to reconcile with passive mechanics. This discovery is being counted as the 12th major anomaly tied to 3I/Atlas since its detection, the latest entry in a growing list that has transformed the object from a transient interstellar visitor into one of the strangest bodies ever recorded. Its story has unfolded like a serial mystery in which each new observation refuses to settle the last. Early on, astronomers were struck by a light curve that shifted too rapidly to be explained by straightforward sublimation, as if the brightness were driven by something more complex than sunlight heating exposed ice. Then came acceleration patterns that could not be cleanly attributed to solar radiation pressure, the standard gentle shove that can slightly alter the paths of small bodies. Observers also noted an absence or weakness of the dust tail one would expect if large amounts of material were being lofted into space, and when its trajectory deviated, the implied force looked uneven and directional, yet frustratingly invisible. As anomaly followed anomaly, 3I/Atlas began to resemble less a passive chunk of ice and more an active agent in its own dynamics. By the time researchers logged the 11th anomaly, an unusual sequence of fragmentation events producing subcomponents that moved in coherent, oddly stable ways, the comet had earned a reputation as the heir to the riddle of Oumuamua, the first known interstellar object, which itself triggered fierce debate about unusual acceleration and geometry. With 3I/Atlas, scientists tried hard to stay anchored to natural explanations. They proposed exotic ice mixtures, layered crusts that might trap and release volatiles episodically, phase transitions in unfamiliar materials, or unusual thermal properties acquired during interstellar travel. Each proposal was a sincere attempt to stretch known physics without breaking it, and in isolation each seemed plausible. But the sum of anomalies, and now this 12th one, has pushed the discussion into a far tenser space, because the jet's stubborn alignment feels qualitatively different from brightness quirks or subtle trajectory nudges. It strikes directly at the mechanics of rotation and outgassing that underlie every comet model in use. Naturally, the first task for serious researchers has been to look for ordinary ways the data could fool us. Perhaps the apparent steadiness is a trick of viewing geometry. If the rotation axis were aligned close to the direction of the jets, a vent might seem stable from our perspective, even while the comet turns. Maybe a specific region of the surface remains continuously sunlit because of the nucleus orientation and orbit, producing sustained outgassing in a relatively fixed direction. Another idea is that complex surface topography, deep pits, cliffs, or narrow fissures, could collimate gas into tight streams, preserving a consistent look in images. Yet every such scenario strains under scrutiny. A jet aligned with the rotation axis should still wobble subtly as illumination changes, and those oscillations should be detectable over multiple rotations. Continuous solar illumination should shift as the object moves and as its obliquity and insolation geometry evolve. Topography alone cannot plausibly maintain million-kilometer coherence for days without the flow spreading or curving. The data resists the ordinary with a stubbornness that keeps pulling theorists back to the core paradox. The nucleus rotates, but the jets act as though they do not. To have jets remain so stable, 3i/Atlas would need either a venting mechanism decoupled from the surface rotation or a way to regulate the outflow in real time to cancel the spin. One speculative natural possibility is that the jets originate not from surface vents, but from deep subsurface conduits that rotate differently from the crust, perhaps because of internal structural layers or differential motion. Yet no known comet exhibits anything like that, and it begins to sound more like engineer machinery than geology. Another possibility is that some exotic composition or magnetic interaction could maintain an inertial reference frame, keeping emissions pointed in a fixed direction independent of spin. But again, no established material process does this in ordinary cometary contexts. Put plainly, if these jets are real and as steady as they appear, the comet seems to be stabilizing its own thrust, actively resisting the torques that should make its emissions sweep across space. That is an extraordinary inference, and even those willing to contemplate it emphasize that extraordinary inferences demand equally extraordinary evidence. Still, the uncomfortable question has been voiced in observatories and forums. Could 3i/Atlas be showing hints of artificial control? The comparison is unavoidable because Loeb previously argued that Oumuamua might be technological debris, perhaps a solar sail or some other artifact, a claim that met strong skepticism from many colleagues. Critics rightly insist that nature is capable of producing surprising phenomena, and that invoking technology without necessity is a scientific failure. Yet the behavior of 3i/Atlas now brushes against a similar boundary, not because anyone has found direct proof of artificiality, but because the jet's fixed orientation resembles directed propulsion in the most superficial mechanical sense. A thruster, after all, does not need to smear with rotation if it is gimbaled or controlled to maintain aim, and the crispness of the jets invites that analogy, whether we like it or not. This does not mean the object is alien technology. It means our current vocabulary may not be sufficient to describe what is happening. Even if the mechanism turns out to be fully natural, it would be unlike anything previously cataloged, perhaps requiring a new class of interstellar comet activity and a revision of how we model the interplay between outgassing, torque, and angular momentum. Traditional comet theories assume that venting occurs roughly from sunlit regions, producing jets that both respond to and alter rotation in predictable ways. Venting creates torque, torque changes spin, spin changes venting geometry, and the whole system evolves in a noisy but comprehensible dance. 3i/Atlas instead shows a kind of geometric order that contradicts that dance, as though the outflow were guided by architecture rather than chance. If the explanation is natural, it might involve layered materials that redirect sublimation through internal channels, compositional gradients that self-collimate plumes, or pressure systems that open and close in phase with rotation to keep a stable line, all of which would be a startling expansion of cometary physics. Loeb has tried to provide a structured way to talk about such departures by introducing a conceptual anomaly scale, a ladder for assessing how far an observation strays from established expectations. Each rung marks a deeper deviation, moving from the merely unusual to the deeply puzzling and finally to what he calls the frontier of technological significance, a term meant not as a claim of alien origin, but as a label for the zone where conventional explanations have not yet found firm footing. On that scale, he argues, 3I/Atlas was already high because its first 11 anomalies made it a statistical outlier among interstellar objects. The 12th anomaly may push it higher still because it seems to demand not just a tweak to parameters, but a rethink of mechanisms. Importantly, Loeb himself has remained careful to stress that science advances through reproducible, transparent evidence rather than through sensational storytelling. His posture is not to declare that the comet is artificial, but to argue that the data should not be prematurely constrained by prejudice about what is allowed to exist. In his view, the danger is not in imagining possibilities, but in dismissing them before the observations have had their full hearing. That restraint is echoed by many researchers who find the anomaly fascinating, yet insist on patience. The investigation, accordingly, is intensifying. High-resolution monitoring from ground-based observatories and space telescopes is being organized to track jet evolution over multiple rotations with finer temporal sampling, testing whether the stability persists or subtly breaks when viewed closely enough. Spectroscopy is being used to search for chemical signatures that could distinguish ordinary water-ice vapor from dust-dominated jets or metal-rich emissions, which might point to unfamiliar compositions. Radio observatories are listening for any coherent or repeating emission patterns, though none have been detected yet, and even a null result will help constrain models. Theorists are simultaneously building dynamic simulations to see whether any configuration of vents, internal cavities, or thermal cycles could reconcile the observations with conservation of angular momentum and energy. Each of these tests could either deflate the mystery by finding a clever natural cause or deepen it by confirming that no such cause fits. Either outcome would be valuable because 3I/Atlas is already forcing comet science to confront the edges of its assumptions. Meanwhile, as the comet continues along its path, there's an added tension. Interstellar visitors do not linger. 3I/Atlas will eventually fade and slip back into the dark between stars, leaving us only the data we manage to gather now. That time pressure heightens both the excitement and the caution. The broader reflection emerging from this episode is that the universe still holds surprises sharp enough to pierce our certainty, and interstellar objects, forged in other planetary systems and shaped by long voyages, may carry architectures or histories that differ fundamentally from those we have learned in our own solar neighborhood. 3I/Atlas has become a kind of mirror for human curiosity, asking whether we will stretch our models to fit the data or allow the data to stretch our models. The 12th anomaly, jets that do not smear with rotation, that remain narrow and fixed as though locked onto some invisible coordinate, stands as the most dramatic chapter yet in that unfolding story. It has turned disbelief into calculation, driven astronomers to recheck their rotational models and reanalyze their images, and stir debates that range from the intricacies of subsurface thermodynamics to the philosophy of how we recognize the unfamiliar. Whether the jets ultimately yield to an exotic but natural explanation or point to something we have not imagined, the legacy of 3I/Atlas is already taking shape in our equations and arguments. It is a reminder that knowledge is provisional, that even the most established mechanics can be challenged by a single stubborn object, and that the cosmos may speak in dialects we have only begun to decipher. 3I/Atlas has become a lightning rod for comet science because its latest behavior seems to contradict the basic link between rotation and outgassing. Astronomers report that the comet's jets stay rigidly pointed in a fixed direction in space, even while the nucleus spins once about every 16 hours. In an ordinary comet, jets produced by sublimating ice would sweep around with the surface, smearing into spirals or broad fans over a single rotation. Instead, these plumes remain narrowly collimated and stable for hours to days, extending more than 1,000,000 kilometers and moving at hundreds of meters per second without showing the curvature that rotation should impose. This unsmeared jet effect is now labeled the 12th anomaly in a growing catalog of puzzling traits. Unexpected brightness shifts, unexplained accelerations, weak dust signatures, and strangely orderly fragmentation that have made 3I/Atlas the interstellar successor to the mystery of Oumuamua. Researchers have tested mundane explanations, such as viewing geometry, axis alignment, or topographic channeling, but each falls short of accounting for such long-lived precision. If the observations hold up, they may imply an exotic natural mechanism not yet recognized in comets. Or, more provocatively, a form of active stabilization reminiscent of controlled propulsion. Either way, 3I/Atlas is forcing a rethink of how jets, torque, and spin interact in icy bodies from beyond our solar system.